Hi students, welcome back to my next video class 15, same chapter. Today we will take up torque on an electric dipole. Students, you can learn this only if you practice last 4 videos. Video 10, 11, 12, 13, 14, it is 15th one. You have to remember all those things. Based on those only we will continue. Look at the heading. This is one of the important 3 marks question in your examination. Put a star in your notes. Keep your notes open while learning this. Torque on an electric dipole. What is torque first of all? Torque is, as you learned in the first year chapter, torque. What's torque? Torque or turning effect of a force. Turning effect of a force on a body. How do you measure it? You measure torque as a product of force multiplied by perpendicular distance. What is this? I explained you in detail last year. Let's have a quick revision of that. See students, I fixed this duster here so that I can easily rotate about this point where my fingertip is. I apply forces like this. Look here, not one force. I can rotate using one force also, but in our discussion, 2 forces together. One finger pushes it down, the other up. See here, like this. One force acting this way, the other force acting this way by the thumb, the other forefinger at these 2 points. The body, I write the body as a line stick. This is the duster. One end experiences a force down, the other up. Let me call this point A, this B. It is rotating about a point O, sometimes the center of the body. Now, the point is very simple. Since I am applying equal forces, sometimes unequal forces, a slightly different story. There too, there will be a rotation. Equal forces together are called couple. Couple means 2. Equal unlike forces always rotates. It's actually a clockwise rotation. Clockwise torque, anti-clockwise torque. If I reverse the forces, anti-clockwise. To distinguish between 2 types of torques, we use sign. We consider torque as a vector. By using right hand screw rule, we denote that or identify that. How do you know the value of torque? Torque as force. 2 forces. Which one you have to consider? Magnitude of either this or this, both are same. That's why consider one force F into perpendicular distance. What is that? AB. This is also called arm length, moment arm. So force or arm of the couple, force into perpendicular distance. This is torque. Torque is a measure of amount of rotation produced. See students, in the case of dipoles also, quite often you see torque experience due to external field. That's what we were learning in the beginning, right from the beginning. The electric force, electric field affected by medium, external medium. When you apply electric force or field from another source charge, there will be force acting on the molecules of the medium. Because of the force acting, the molecules rotate. Torque. In order to understand that in detail, in the forthcoming units chapters, we are learning here the torque and the dipole, single. So here, what you have to consider first? Let us consider this region contains electric force or field. Here just force applied by me. Here force due to charge. Where is the charge? Let us suppose some charge distribution like this. So far we learned unit charge, but here I consider a charge distribution over a surface like this, say positive charges. You just suppose this way. You need not write in the exam while answering this question. You need to remember how electric field is produced by a charge distribution like this. These are positive charges. These together produce electric force in this region. How do you identify electric force field? For that you consider a charge. Which charge? Unit positive charge or unit positive test charge. You place anywhere in this region a unit positive test charge that experiences a force. Which way? As this is also positive, positive repel, there will be force acting this way. Let us suppose this entire region contains almost same value of force and same direction for simplicity. Sometimes it is the case, sometimes quite oftenly, in this case not same. Why? This is at a distance. If you consider a point somewhere here, a lesser distance, force must be more. But let us suppose this region contains same field, right? If I place unit charge here, here also it experiences force to the right. If I place unit charge here, here also it experiences to the right. Everywhere in this region, the unit charge experiences force to the right. That's why field is to the right. I write electric field is to the right of you in the board to the right. In this region, instead of unit charge, I place a dipole. What is a dipole? Two equal unlike charges separated by a certain distance. This is a dipole. This is, say, positive end and this negative end of the dipole. Let me consider this minus q charge, end A, and this end B with plus q charge, What is the separation between positive and negative charges? S denoted by length 2a. This length is 2a, remember students. And always you assign direction to the dipole. Which way? S, we have to remember. From minus q to plus q. It's called dipole moment vector. To show rotation, all that we use it. This is the center of the dipole. Now, this is the direction of electric field. Electric field is acting this way. Remember students. Right to the right. Now, if I place unit charge here, it experiences force to the right. This positive charge, that also experiences force to the right. Yes. Let me write that force F plus Q to tell you it is force on positive charge. How to find that force? Since you know electric field, how did you define electric field, dear my students? Dear students, force per unit charge. What is force then? Force F equals to Q into E. Since you already know the electric field value here, how do you know the force? Charge into field. See, this is very first application of this formula, this kind. You wrote expression for electric field 1 over 4 pi epsilon 0 Q divided by R square. Use that to solve problems. Now, we are using another way. Straight away definition is used here. What is definition? Force per unit charge. If you know electric field, how do you find force? Charge into field. Remember this. I write now charge Q. There are two types of charges which are there. Plus, this is positive charge. See, this is positive implies electric field is same as force, or force is same as electric. This is the direction of force. Force is same as electric field. See, electric field and force are in the same direction, positive. Now let's come to negative charge. This negative charge, see here, attracted toward this positive. So you have to write arrow this way. Very good. Right? There is arrow pointing to the left compared to this. Electric field is right, force is left. Why, students? Because being negative attracted towards positive charge distribution. That's why if I write F minus Q, that is minus QE. Don't be panic. Strange. Why? Because electric field is force per unit charge. What is force? QE into E. Very simple. Use this way. Henceforth we will be using this way. Very important. So write this. F equals to minus Q into E to the left. Students, one end of the molecule experiences force to the right, the other end to the left. Like this. One end of duster force acting down, the other up. Together produce torque. Here too, these two produce torque. How do you measure torque? Force multiplied by perpendicular distance. Force perpendicular distance AB. Similarly, we have to show perpendicular distance. This is line of action of force. This is another line of action of force. Between these two you show direction. You can show here also, everywhere. But if I start perpendicular from here, it has an advantage in the diagram. Why, can you guess? Yes, this is corner B, corner A. If I call this corner C, what is the shape of this? Triangle. You can use properties of triangle. That too, right angle triangle. Very good. If I consider this as theta, what is theta? Angle between direction of electric field, this electric field direction, remember, same direction everywhere, and dipole axis or dipole moment. See here, dipole moment is pointing up, slightly slant. Electric field is to the right. What is the angle between them? Theta, shown here, right? This becomes what? Opposite side. This is, I write this color, orange. This is opposite side. And this is adjacent side, right? Students, as we learnt in the previous video, what is opposite? Whenever I use the word opposite, hypotenuse into sine theta. Very, very important, interesting. You must write hypotenuse into sine theta. What is hypotenuse? Hypotenuse is 2a, very good, into sine theta. So, perpendicular separation between directions of action of f plus q, f minus q is 2a sine theta. You need it to find torque. What is torque? Force into perpendicular distance, friends. You have learned there are two forces acting, one f plus q, the other f minus q. They are acting at a separation 2a sine theta. Pure trigonometry, right? You write this diagram, practice 2-3 times as it is. Watch 2-3 times, practice. You will get, or you can know how to write. Now, students, now by definition, let us find torque acting on it. By definition, what is torque? What is torque? Torque is again this force multiplied by perpendicular distance. Perpendicular, I write this way, perpendicular distance. I will remove this. I will write it once again for you. So, I write torque tau equals to, what is force? There are two forces, F plus Q, F minus Q. So, here force is F plus Q or F minus Q, either of the two. If I write this, how do you read? Magnitude. Magnitude of plus Q or magnitude of minus Q. So, I write F. What is the magnitude of plus Q or magnitude of minus Q? QE. Very simple. Why? Because F plus Q vector is minus Q. F minus Q vector is minus QE. F plus Q is plus QE. You just use the value, only value. That's why magnitude is QE. Into perpendicular distance. What is perpendicular distance? Come on, look here. A, B, B, C, C, A. In this, BC is perpendicular distance. BC. Look at once again. This is perpendicular distance between lines of action of the two forces. One force is acting this way, the other this way. Between these two lines of actions, the perpendicular distance is BC. So, tau equals to, what is F? QE into what is BC? Look here, BC. BC is 2a into sine theta. Once again, for your clarity in the explanation, I write this diagram once again. This is the end A and this is the end B of the dipole. This plus Q end and this minus Q end. This is the separation between these two, 2A, right? One force acting like this, that is F minus Q, and this F plus Q, right? These two are lines of action of the two forces, perpendicular distance. This is C, angle theta. What is this side? Opposite. What is opposite? Hypotenuse. 2a into sine theta. Remember this. You say 10 times. What is hypotenuse? 2a. What is opposite side? Hypotenuse into sine theta. What is adjacent side? Hypotenuse into cos theta. Whenever we say opposite, hypotenuse into sine theta. Hypotenuse 2a. Adjacent, hypotenuse into cos theta. That's it. So, tau equals to, I write 2a into q into e sine theta. What is 2a? But I write here 2a into q. What is that? P. Very good. Dipole moment. Dipole moment. We can write dipole moment. Dipole moment. Short. In short, I write MOM. So, tau equals to P into E into sine theta. I wrote P sine theta. This is the magnitude form of torque. Vectorially, as both P and E are vectors, vectorially we write tau vector equals to P value of dipole moment, E value of electric field, sin theta into unit vector. Now look at this, students. This is the direction of electric field in the diagram. See once again there. And this is the direction of dipole moment, right? P. So this is the angle theta. So these two together produce rotation of the dipole, that is shown by using N. This is similar to your cross product. What is cross product? A cross B. A cross B. What is A cross B? Value of A, value of B into sin theta into unit vector N. What is unit vector? Unit vector is perpendicular to plane containing value of A, value of B. If you take this A and this B, then you hold right-handed screw here and give rotation from A to B. So direction is perpendicular into the board. If you define B cross A, perpendicular and out of the board, like this, perpendicular into the board, perpendicular out of the board. That's why tau equals to right vector P like vector A cross vector E like vector B. P cross E, A cross B. What is A cross B? A B sin theta. P cross E, P is sin theta. So after all, what is this? If this is a dipole, one end experiences force like this, the other end like this. These two together rotates like this. Rotation is shown like this, like rotating a right-handed screw. See, this is right-handed screw. Right-handed screw holding here and rotating like this. In that direction it rotates. If you reverse forces, rotates like this. You have to hold it like this, giving rotation like this. When one force acts this way, the other force acts this way. Rotation like this, rotation like this. There are two rotations. Rotation clockwise, rotation anti-clockwise. So this is clockwise rotation. P cross E, P sin theta. This is vector idea you have learned. Very simple, students. How do you explain it once again? Consider a dipole. Consider a dipole having charges plus Q and minus Q. Charges of dipole. Charges of dipole in uniform field. In uniform field. Field means what? Electric field. Electric field E. Making an angle theta. Making angle theta with respect to P. What is P? Dipole axis or direction of dipole. Direction of dipole is from minus P to minus Q to plus Q. Like this. Electric field is like this. What is the angle between them? Theta. Right? Force on plus Q. F plus Q. What is that? Plus QE. And force on minus Q. What is that? F minus Q. That is equal to minus QE as shown in the diagram. Right? The two forces together produce torque. Means rotate the dipole. What is the aim of the torque? To align the dipole in the direction of the field. See, electric field is like this. Pushing one end this way, pulling the other like this. Aligns the dipole like this. This alignment, orientation is the effect of external field. Students, molecule rotates and aligns itself in the direction of the field. Very, very important topic. We will use it in next chapter, right? What is the effect of torque? Torque rotates the molecule, aligns itself in the direction of the field. And that torque is due to force acting at this end, positive end, plus QE. And you remember this also. How did you get this relation? Don't wonder. What is electric field? Force per unit charge. So solve for force QE. That's it. This plus QE, positive charge, minus QE, negative charge. So if plus QE is right, minus QE left. That's it. These two forces together produce a torque. What is torque? Force into perpendicular distance. That is F into BC. What is F? QE. What's BC? A sin theta. 2A sin theta. How? See this diagram. I have written this separately here. F minus Q, F plus Q, and this is the perpendicular separation, 2A sin theta. So it is QE 2A sin theta or 2AQ into E sin theta. What is 2AQ? P. What is P? dipole moment. The rest very simple. Practice this, one of the 3 marks questions, and also very important as far as next part of physics you will be learning is concerned. It is very much oftenly used in next topics also. Whenever we use torque on a dipole, you think like this: there will be a molecule with positive negative ends. They experience forces in the opposite direction in external field. Because of that, it rotates and aligns itself in the direction of the field. And that is discussed like this. 3 marks question and very important. Write 2-3 times. You will practice. You will see next. Okay students, we will see one more topic in the same video, that is electric field line. I will talk about this little bit when I introduce electric field. What is field? How to represent field, as field is a vector quantity having both magnitude and direction. How to represent field I explained you. Now we will see the representation of field line. Representation of field line around a point charge first of all. Then I will come to the word what is field line. Students, you know what is a point charge? Point charge is a charge whose dimension negligible but charge value large. As I told you, this region contains its influence. What is that influence? A force. How do you find that force? By bringing another charge near it. Which charge we chose? Unit positive test charge. Why test? Used to test the presence of field due to this. So, if I bring another charge which is also positive, test charge. Why test charge? The value of this is very small compared to this. That's why it is test charge. Presence of this doesn't affect the charge configuration and field strength here. Such a small. I give an example, right? A drop of water is negligible in front of mighty ocean. Drop of water like a unit, like this charge, unit charge. Now, as both are positive, what happens? It gets repelled, tends to move outwards. If I come to this point, bringing this here, what will happen? Here also it experiences repulsion, but valueless. Why? You know, electric field value, which is a force per unit charge, and you wrote a relation 1 over 4 pi epsilon naught q by r square, the value inversely proportional to square of distance. As you move away from the charge, distance increases, the value of electric field decreases. That's why I write shorter arrow. This is longer arrow. The length of the arrow proportional to magnitude of the field. And I have shown direction. If I come over to this point somewhere farther, will be still lesser. I write still shorter arrow. I can do the same this side also. Here, right? Here, when I place unit charge, tends to move outwards. If I place here, tends to move outwards. Here also tends to move outwards. But the length of the arrow, this longer than this. Why? As this point is nearer, electric field is greater. This bit farther, electric field lesser. Still away, still decreases. The same story here too. We can write electric field along with directions. I can represent like this. Students, I am representing the variation of electric field all around using directed line segment. Right? A vector, arrows. You can do all around like this. If I join all the 3 arrows together, that is field line, a field line. A field line. This is also field line. Like this, I can write one more field line here, 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 one more field line. At this point, another one here, also here. What all these field lines represent? All these field lines represent the direction of motion of unit positive charge when placed at each point, here, anywhere. You can write one more here. Wherever you see bit more gap, you can write one line there. How many lines you can write like this? Infinitely many. Can be writing forever like this, right? So this is the field pattern. This gives the clear visualization of electric field. What does each line represent? The direction or path along which a unit positive charge tends to move. So what is field line? A path along which a unit positive charge tends to move at that point in an electric field. It can be a straight line like this or curved one. I will show curved one next example. This is for a unit positive charge, field pattern around a positive charge. Now if you consider negative charge, I place negative charge somewhere here, minus q. If I place minus q charge and unit positive charge at a point somewhere here, if I release unit positive charge, gets attracted towards it, why? Positive, negative attract each other. Place this unit positive charge bit away from source negative charge. What will happen? It experiences force bit lesser compared to that here. Here still lesser. That's why I'm writing shorter arrows. Same story that you did here. So if we join all the lines or arrows, we'll get a field line. Here towards my negative charge. Here towards negative charge. Towards negative charge. Towards negative charge. Towards negative charge. Here see towards negative charge. Towards negative charge. Towards negative charge. So all field lines moving towards negative charge. In fact, you can say the field lines converge at negative source charge and diverge from positive source charge. Diverge from positive source charge, converge at negative source charge. Where do they end? If you start writing, where do they go? They go to infinity. You cannot define a point where it has come from, or you cannot define a point where it goes, or you cannot say where it meet a point. No, never ending. So you can say the field lines start from positive charge, end at infinity, goes to infinity. Here field lines end at negative charge, start from infinity. Start from infinity, end at negative charge, and start from positive charge, end at infinity. This for single point charges, positive and negative. Now you will see what happens to the pattern of line of force or electric field lines when two charges considered, 2 point charges. Here single positive charge, electric field lines diverge, start from positive, end at infinity. Here they start from infinity, end at negative charge. When you consider a positive and negative together, what happens? Positive and negative. Where did you see the students? S in the case of a dipole. Now I place a unit positive test charge. What happens? Due to the repulsion from this, attraction from this, move straight to this point charge. This starts from positive charge, end at negative charge. Here start from infinity, end at negative. Here start from positive, end at infinity. Now consider the same charge here. This charge positive, as it is very close to unit positive charge, kicks it out. Go like this. When it moves somewhere here to the point, this charge attracts towards this. This repels, this attracts. I have written longer arrow for this as it is closer. I have written shorter arrow for this as it is farther. You find resultant of these two. This is the resultant direction. You come to this point. Here again two forces. One towards this, the other away from this. Resultant will be somewhere like this. So if you continue like this, you will show field line like this. Again starting from positive, ending at negative. Like this, like this, like this. At each point on the curve, a straight line, there is a curve, bent line. You come to this point. How you have got this line? Very simple logic. This is the point where, okay, this is the direction of the resultant, right? Like this, you can find resultant at every point. You draw one more line like this. Initially starts moving out because the influence of this takes a bend. Then you can trace it out like this, like this, like this, like this. They start from the positive charge, end at negative charge. An important property of field lines. See, field lines straight, field lines curved. In the case of a combination of positive and negative, equal magnitude. If magnitude is not equal, then the concentration of field lines changes. Here almost same lines around this. Now what happens if two like charges may be positive or negative, both positive, both negative considered. Very interesting. If you place a unit charge near this, because of the repulsion starts moving out, right? It moves outwards, comes to a point, midpoint. Exactly at the midpoint, it experiences forces which are equal and opposite. Force due to this, to the left, same force is exerted by this, to the right. That's why the two forces cancel each other, and that point corresponds to what? Nothing. There will be no net force. Such a point is called null point. Very, very important in the electrostatics. Null point. What is null point? A point or region where resultant electric field is zero. One such example. Now come to a point somewhere like this. Here the field line takes a deviation like this. This is the curve representing field line. A curve representing field line. Curve representing field line. Curve representing field line. First let us write how it will be. I'll explain. I'll give explanation for this. For example, why field line takes a curve like this? Take this point. At this point, this charge repels it, and this also repels in this direction. What is the resultant of these two? If you construct a parallelogram, as this is bit away, this is nearer, the force due to this less, force due to this more. If you construct a parallelogram, you'll get the resultant like this, tangent to this curve. The same story can be explained for all. The electric field resultant. What is the resultant? If you come to this line of force or field line, this point, this charge repels, this charge also repels. This is the resultant direction. At this point, resultant direction. At this point, resultant direction. What are all these? Tangents at each point, right? You can write lines of force like this. This, and continue like this. These are the field lines in this space, region, in which two like charges situated. Here again, you have considered same magnitude. We can write similar lines of force, similar pattern, even if you consider unequal magnitude like charges, and the concentration of the field lines will be more towards larger charge, and concentration of field lines, number of field lines will be lesser towards the weaker charge. That's the point you have to remember. Field pattern for like charges, unlike charges, and this point negative, point positive. Like this you can represent field lines. Each field line is a direction along which unit positive charge tends to move. So what is electric field line? It is an imaginary path along which a unit positive charge tends to move. That is called electric field line. And I have discussed some important points. Therefore, I'll summarize my discussion, and that will be one of the important 3 marks question examination. Let us name properties of field lines. Some important properties of field lines. One important property we have learned: field lines, electric field lines, or just field lines in the chapter, start from, can you guess? Yes, start from which charge? Start from positive charge. Start from positive charge, and end at infinity. Yes. So similar word if you say, the field lines start from infinity and end at negative charge, end at negative charge. See here, diagram. If you consider both positive and negative together like this, how do you say? Field lines start from positive charge and end at negative charge. When you consider positive and negative together in a region, a system of positive and negative together, they start from positive, end at negative. An important point. And one more point, the field lines are continuous curves. See, continuously they are extending from infinity to negative charge, from positive charge to infinity, here from positive to negative. However, if there is a charge in the region, then there will be discontinuation. These are continuous in a charge free region, continuous. Electric field lines are continuous. We will learn about this in detail next. Continuous in a charge free region, right? Very important topic. I will explain you about that little bit in detail in next sections. And another important, students, very important, for 1 mass normally it is asked, and is one of the differences what I am writing a point now. One of the differences, major differences between electric field and magnetic field, that is field lines. I write ditto. Ditto means what? Electric field lines do not form loops. They don't loop around positive charge, negative charge, or positive or negative charge combination like that. You will know why in detail later on. And in an electric field, two charges do not intersect each other. Very important. I'll write that point here. Two lines, sixth one, two field lines do not intersect, cut each other, intersect each other in an electric field, in a field. In an electric field do not intersect. If they do, what happens? Which means there are two directions for one field, which is not possible. Students, can you kick yourself alone a football in two directions? No, right? You can kick only in one direction. You have two legs, but you cannot kick in two directions, right? One person kick only in one direction. Similarly, two directions cannot exist for one electric field. Very important. Remember this. Very important. No? All these points very important. One of the expected questions in our examination, board examination, field lines start from positive, end at infinity for single point charge. They start from infinity, end at single negative charge. If you consider a positive negative combination, start from positive, end at negative. For two positive I showed, and one more, they do not form loops. Very important, do not form loops. They are continuous curves in charge free region. If another charge does not exist, it continues, electric field continues. There are some more points to be learned about that. You keep that point in mind for now. Last one, very important, the field lines do not intersect each other in an electric field. Very important. So go through the study material is there in my notes, page number 10 and 11. We will continue with the same topic, very important, that is electric flux, Gauss law. Is a continuation of what we have learned. I will take through all this once again in my notes in the next video, right? Till then, you prepare all this very well, right? Bye.